Hello, everyone. Thanks for joining us today. We're going to talk about collections, and the speaker today is Luca, and he will walk you through the various fundamentals of collection and tell you how you can use collection in your work. Luca, please start.
Okay. So today we are going to introduce Java collections as a topic, and we are going to talk about these objects, container objects, for other objects, and which is provided by the Java language. Who am I? I am Luca Belluzzi. I'm senior software engineer at EPAM, and I've been dealing with Java for the last 17 years now, first at university and then on the job. And most of the knowledge I'm going to share with you today is actually well established and well known. You can find a bunch of source of informations on the web via books and the likes, but I will try to give you some personal advice when it is the case. So this is the agenda. We are going to split the agenda in two parts. Today we are going to discuss the first topics, the first part of the agenda, and then we will have another talk for the second part. And first we are going to discuss what the data structure is, and then we are going to talk about arrays, probably the simplest data structure, and then we are going to talk about linked list in a couple of flavors, single pointer linked list and double pointer linked list. Then we are going to talk about stack, queue, hash map, hash set. And the very last topic is about concurrency. And we are going to discuss some, let's say, situations, introduce the concurrency problem and see how to solve it when it comes to use collections. So what is a data structure? First of all, we have to introduce a concept, and the concept is an abstract one, let's say a high-level concept, and it's the concept of abstract data type. Now, an abstract data type is a mathematical model with a collection of operations defined on that model. Sets of integers together with the operation of union, intersection, and set difference form a simple example of an abstract data type. Now, don't focus too much on the mathematical model part. Just keep in mind the example. Sets of integers together with the operations of union, intersection, and set difference form a simple example of abstract data type. And given that we have this specification, this definition of abstract data type, we can talk about data structures. So what are data structures? Data structures are used to represent the mathematical model underlying an ADT, an abstract data type. And so data structure are collections of variables. Here collection stands for ensemble, set, but not in the Java meaning of the term. Collections of variables, possibly of different data types, connected in various ways. If you go back, if we rewind a bit, collections of variables, this is clear. It's just as an ensemble, a set of variables, possibly of several different data types, quite clear, I would say. Connected in various ways is the key to the understanding of a data structure. So a data structure is related to data and it has a structure, and the structure is defined on how the elements of the data structure are connected among each other. So let's switch to a second definition for data structure. A data structure is a collection of elements, fine, and the relations among the elements, which define the structure itself, and the operations. So the data structure is not only, let's say, a set of variables connected to each other, but it's also the set of operation which is defined on that data structure. So if you focus on the picture on the right, you can see this simple example of interconnected elements. And we might say an example of element might be that x is an integer. So a collection of elements, an example elements might be x is an integer. An example relation among elements, x and y, might be father y is x. So if you see y is connected to x somehow, we will see later how to do that in Java, but I can define a relation of parenthood between x and y. So father y is x. This is an example relation. An example operation might be an add all from a data structure 2 into a data structure 1. If we think about the set example related to ADTs, so if the data structure we're talking about represent a set, the add all operation would be the union of two sets. And let's check out a simplified version of ADT to start understanding it. And it is as follows. An ADT can be seen as a mathematical object composed by two sets. The first set is called domain of the type, and it collects the possible values for the type under definition. The second set is the one of functions, which defines the operations that can be performed over the values of the type. And we have an example here. The Boolean abstract data type is defined by two sets. The first set is the domain of the type, true or false. So whatever we capture in the domain of the type, every possible value for the new type we are defining. So we want to define the Boolean type. First step, we have to understand all the possible values that the type can assume. And in the case of Boolean, this domain is true or false. The other set is the set of operations, and or not. But we have to add also this sentence here, where the operations have the usual meaning. So when we write down an abstract data type together with specifying the domain of the type, when it comes to operations, we need to also specify the meaning of the operation. So the what part of an operation. We never specify the how part, so how to implement it, but we must define the what part, so what the function does. And an ADT allows to specify data, objects in the world of Java, in an abstract way, without assuming a given programming language. So an ADT is not dependent on how data are represented. An ADT is not dependent on how the functions are implemented. So just keep this in mind. We want to define a new type for the data. We need to understand, first of all, the possible values that the data can assume, the domain of the type. And we have to define the operations on that domain with their meaning. And this is a more, let's say, advanced ADT, a more advanced abstract data type, which is the Q1. And the QADT represents sequences of elements of a given type T, which are FIFO managed, which means first in, first out managed. So again, we define, in this case, two domains. The first domain, the domain Q, which is the set of all possible sequences of elements of type T. And we also specify that the empty sequence is part of the Q set. And T is the actual domain, is the set of the possible values for an element in the Q. And when it comes to specify the functions, as an example, the isEmpty function for the Q, we need to specify the header. In this case, isEmpty has Q as argument and returns a Boolean. And then we have to specify preconditions and postconditions. This is the how part. So what does the function do? We need to specify it in an ADT. So preconditions for the isEmpty function is none. Postconditions, result is true if Q is equal to the empty sequence, false otherwise, and so on and so forth. As an example, you can see with a Q function specification, in the postconditions, we have that the result is the Q that is obtained from Q, from the input argument, adding the element also as received as input argument, and the result, the element is the last element in the Q. This is capturing the first in, first out policy, partially because the other part is going to be captured by the specification of the dequeue function, the one that takes something out of the queue. So beware that when we talk about Java interfaces, we have a bunch of information on the web which refers to Java interfaces as ADTs. It's wrong, because an ADT is not only composed by function headers, an ADT is composed by domain definitions and has to specify for every function preconditions and postconditions. So when it comes to implement an ADT, we have a situation as follows. And we can see that, first of all, we have an interface which defines the functions on the ADT of the ADT. And then we have an implementation. A data structure is basically in the implementation part of an ADT. So the overall implementation, the overall data structure, is composed by the interface, the operations, and the structure itself. So a data structure is a collection of elements and the relations among elements and operations. So it's all together, all this set of things is the data structure. And in this case, you can see as an example that we have a sequence here, which is a quite common, a list, let's say, which is a quite common structure for data, okay? But it's not the whole story. You also have to consider operations and the interface. And what the user sees, the user of the data structure, is the interface. So I know that some of you already have used some collection in Java. So as an example, you might have used a linked list via the list interface. And this is basically what's behind. Some, let's say, concepts altogether. We are, generally speaking, elements in a data structure can be of any type. When elements have homogeneous types, the data structure is said to be homogeneous. In Java, it is possible to specify the type using generics. If you have used collections, you should know that when you actually instantiate it, you have to specify the type you are going to store inside. And if you don't, you get a warning from the Java virtual machine, okay? And some collections are said to be ordered, which means that given two elements, we can assert that one of them is before the other in the collection. An example of such collection is the list. Some other collections are not ordered. An example of such a collection is the set. So a list is something similar to what we see below here in the picture. We can see that we have two lists, one on top of the other. And the first list so if you examine the lists, the structure, you see that you can identify the first, the second, the third, the fourth, and so on element. This is what makes the collection ordered. In a set, you wouldn't be able to do that. And in some cases, it is required the existence of a relation of ordering among elements. As an example, in search trees, I'm going to go a bit deeper on this on the next slide. But keep in mind this last point. An ordered collection, like a list, might contain elements out of order with respect to their order relation. So we talk about ordered collection when we can identify a first, a second, a third element, and so on. But it doesn't mean that what you put inside is actually ordered in terms of the relation of order among elements. So if you check the second list, you can see that the values are not in order. And this is perfectly legal. Despite the collection being ordered, you store elements inside in a not ordered way. And we can solve this problem if we want an ordered elements in an ordered data structure. Okay, let's go back to this point here. In some cases, it is required the existence of a relation of ordering among elements. As an example, in search trees. Search trees are non-linear data structures. We can actually divide data structures in terms of their structure, how they are structured actually. So if there is a hierarchy, as in this case, in the tree case, we talk about non-linear data structure. Otherwise, if the structure is linear, so you can just move from one element to the other linearly, we talk about linear data structure. So the list, the one on the right, is a linear data structure. The tree, the one on the left, is a non-linear data structure. And we were talking about ordering of elements, and you can see that elements in the tree are organized in such a way that given a value in a node, so let's start from the root here, 78, every value in the left subtree is smaller than 78. And every value on the right subtree is greater than 78. And the same holds if you go in the subtree itself. So if you go to 50, every value on the left is smaller, every value on the right is greater. So we are kind of keeping this kind of organization for elements inside the tree. And why we do that? Because we have to speed up the search problem. So let's try it out. Let's try to find the element 82 in the tree. We would start from the root, and given that 82 is bigger than 78, we know that if the value is there, it must be on the right subtree. So we move right, and we get 89, and we compare with 82, and we know that 82 is smaller than 89, so it must be in the left subtree, and we move left, and we find the element in just 2 steps. If you do the same thing in the list, you can see that something like 1, 2, 3, 4 steps are required to find 82. And if you want to find 97, it would get even more. In the tree, you can find whatever value, if it's there, in just 2 steps. And of course, in search trees, insertions and deletions must keep the tree balanced. The key here is that we need to keep this tree balanced. So if we insert elements in the wrong way, we wouldn't have the tree looking like this, so that every leaf of the tree is at the same level, or as an example, 1 level less. But we could have a degenerated tree which would look like a list. it would be possible. If I put 97 here as the root, every value goes in the left. And if I would put 89 here, every value goes in the left, and I would get a list here. And this is not legal for balanced trees, okay? Search time is logarithmic for the tree, and this is, let's say, due to the structure of the tree itself. And the time for search time is linear for the list, because you have to scan all the list in the worst case. So previously we were talking about out of order elements in a data structure. And here we have an example. This is an array. It's an ordered data structure, but we can see that elements inside are not ordered. If we want them in order, we can sort the array. And this is a common operation that can be done. And another common operation is iteration. And iteration scan the collection in a given order if the collection is ordered. Otherwise, no other guarantees. So when we iterate over a set, as an example, we might get elements in a sequence which is not ordered, because there is no order concept in a set. This is a snippet of code which shows you how to iterate over a set. And other common operations, of course, we are talking about containers of elements, so we can add, remove elements, we can retrieve elements, and check for presence. And every data structure has advantages and disadvantages in terms of performance when it comes to perform this kind of operations. And the other option for actually scanning a collection is to use streams, which are out of the scope, but I suggest you to take a look at Java streams when it comes to, as an example, loop over the data structure and scan the data structure. And we can actually sort elements in a data structure, but elements must be comparable. What does it mean? If you see the picture here, this is an array. We can assume, as an example, that it's containing geometric shapes. So how would you sort this array? We don't know, as long as we don't have a way to compare an element to each other, to the other one. As an example, we could define a custom comparator for the shape object, which calculates the area of the object. And in that way, you would be able to sort them using the area criteria. So we might also use a different criteria to sort an array or elements in a data structure. The key to understand is just that you have a chance to define comparators when it comes to sorting. Okay, let's start with the first collection interface, which is the set one. And we would like to capture the mathematical concept of set. And I already told you that an interface does not capture entirely the concept of ADT, but what I want to show you here are just the operations and the main concept about sets. So no ordering, so elements in a set are not ordered. No duplicates. This is because we want to capture the mathematical concept of set. And in the mathematical concept of set, we don't have duplicates. We have an operation for the union between two sets. We have an operation for intersection, which is retain all. And we have an operation for the difference between two sets. Of course, remember that an interface does not define how to implement the behavior. So to make a tricky example here, if we go back to the slides here, let's think about the set interface. You have the set interface here. It only defines the function add all, remove all, retain all, and so on and so forth. And then here you can implement it, as long as you respect the contract, let's say, in terms of interface and the meaning of the functions, most importantly, then you can do whatever you want inside. As an example, you might use an ordered collection, a list, to implement an unordered collection, the set. You could do this just ignoring the order inside the implementation, okay? And the other interface is the list interface, which is something like the one you see here below, depicted here below. A list is a sequence of an ordered sequence of elements, and every element has a position. And we do have the concept of ordering among elements. You can always say, given two of them, where it is and who is before. We might have duplicates, depends on the implementation, so the interface does not force the absence or presence of duplicates. And then we have these functions here. We can add an element. We can add an element at a given position. We can get an element at a given position. And iterator is something which comes from the iterator interface, and it's I show you before the snippet of code. It's a method that returns an iterator object to scan the data structure. And then we have a more specific method, the list iterator, which is specific to the list, which is something like has a special feature, which is the one that we can iterate in both directions. And it will be clear later why it is possible to iterate. So basically scan the data structure moving, let's say, left to right and right to left. The queue interface is it captures partially the QADT. I already told you about the first in, first out policy. And the main functions for a queue are offer in Java, which adds at the end, and poll, which returns the first element and removes. So elements are going inside at the end of the queue, and elements are going out at the beginning of the queue. And in practice, we use queue quite often, especially when we talk about message receiving. So every entity and every let's say, as an example, in Apache Storm, in a stream processing framework, we have different computing elements which exchange messages, and usually every element has a receiving queue. So if you want to, element A wants to send a message to element B, element A is going to send the message, and element B is going to receive it and put it in a queue to be processed. So queue of messages are everywhere. This is the stack. This is not an interface in Java. It is a class. And we have a different concept. It is, let's say, contraposed with the first in, first out policy of the queue. In this case, with the stack, we use a last in, first out policy. So elements are added on top of the queue, of the stack, and elements are removed on top of the stack. And these are the function pop and push. The map interface is another, let's say, collection interface, and it's a key value store, a key value storage and retrieval. Keys are unique, and we have these two functions, put, and it's you put a couple, a pair, a key value pair, and then you get using the key, and you get the value. So as an example here, we just add key 6 and pig into the structure, and we have it here, and then we get with key 3, and we get cat. And note that we don't have ordering here, so elements are not stored in order. And arrays are the let's say simplest data structure probably. And what is an array? An array is a sequence of numbered indexed slots. What does it mean? Well, slots are contiguous in memory. So in memory, you have a piece of memory which is booked, is statically allocated for the array, and then it is divided in slots, and every slot is numbered in this way, starting from 0, 1, 2, 3, 4, and so on and so forth. What is the index? Why do we start from 0? Because the index is the displacement from the initial address, and we have hardware support to access any element given a displacement from an initial address. And here it's a bit more clear. So as an example, if I write something like this, something like R3, what I would do is to start from the initial address and go to index 3. So we calculate the address, summing this address with this value. This is why we start from 0, because when we start, we want the first element, we start from the initial address, and we don't have to sum anything. It's just 0, so we are already in the right place. Okay, to read the slot, the syntax is something like this. So string s equals r I, and I is an index. To set a slot, something like this, ri equals horse. Index out of bounds is an exception that you are going to get if you try to access an array using an index out of bounds. So legal indexes for our case here in the example are from 0 to 4. If you use 5 as an example, you get an index out of bounds exception. Okay, question, what is the length of this array? The length of an array is the number of elements. So if you count them, it's 1, 2, 3, 4, 5. So the length of the array is the number of slots, 5 slots, and it's 1 plus the last index. As an example, if you see here to iterate to scan an array with a for loop, you would use something like this equation here, which would say something like the index e goes from 0 to 4. Okay. And okay, the array is a static data structure. What does it mean? It means that when we allocate an array, we need to basically book a certain amount of memory, and then we have a certain amount of slots that we can use. But when we insert and remove, and the situation is dynamic, every time we hit the end of an array, we have to bother ourselves with instantiating a bigger array and copying the old array in the new one, and to make the array dynamic. But this is not cheap. in terms of costs, in terms of time costs. So to overcome this problem and generally speaking, to provide different futures, we have a different data structure, which is the list. So the list is something like this. It's dynamic, so we can add and remove nodes. I will show you later how to do that in the next slides. But it's something like this. So we have a node which contains an object reference to another node, and this is important. If you remember, a data structure is let's say a part of the data structure definition is relations among the elements. How do we define if an element is related to this one? Well, there is an object reference inside that refers the other object, okay? And of course, we need to store data inside a node. So this is an example node. We need some more work here. And the list would keep a reference to the head, okay, to the head node. And then we would be able to implement the operations, such as, again, example, insertion and deletions, following the nodes starting from the head and moving from one node to the other one and implementing our operations. And I will show you next how to do that. So as an example operation is insertion. How do we insert in a single pointer linked list? Let's start from the beginning. So we have a list with 3 elements, cat, dog, and pig. And we want to insert the element horse between cat and dog. So at index 1. So 0, 1, 2. We want to insert at index 1 horse. How to do that? First, we create a new node with the horse inside, with the string horse inside. And then we instantiate the next, this one here. In the node, we have a reference to another object, the next one. We initiate the next pointer to predecessor.next. Predecessor is basically the node which is before the position we want to insert. So in our case is cat. So basically what we are doing is to add this arrow here from horse to dog. And then we cut the link between cat and dog, overwriting predecessor.next. We initiate it, we set it to new node, which is the new node we want to insert. Okay, so first step, from the new node to the, let's say, next initiation. Then we cut and we overwrite with our new node. And the result is this one. So it's a new list. Actually, it's the same list with a node more, where the horse element is in between cat and dog. And this was the insertion. And of course, you have to beware of corner cases. So as an example, insertion in an empty list would be different. Insertion in a list with just one element and things like that. Okay, how we implement deletion? We basically do something like move to the predecessor. In this case, we want to remove dog. So we move to the predecessor, which is cat, and then we basically cut the pointer next to the dog, and we make it point to pig. So the trick is predecessor.next equals predecessor dot next dot next. So we just jump and we skip this node and we cut it out. And the result is a list like this where the node dog is not there anymore. And of course, again, you need to be aware of corner cases. Okay, so this was the first part of the talk. Maybe you have some questions.
Yeah, for now I don't see any questions in the chat, so we can proceed. Can you hear me now?
Yeah, I can hear you.
Yeah, I don't see any questions in the chat. I think we can proceed.
I think the first part is actually over.
Mm-hmm.
We can
Oh,
basically.
yeah, I see one question. Uh, yeah, in which cases you must use an array instead of list?
Well, if you don't have big dynamicity, if you're not expecting big changes in terms of dimensions. So basically, if the situation is not variable, but it's pretty much static, you just use an array. And also, yeah, that's the main point. Yeah.
Okay, yeah, I agree. I hope that answers the question. Yeah, you have the last chance to type anything in the chat if you have a question about what we discussed today. Three to one. I guess no one have questions, so yeah, we can finish our today's session. Thank you everyone who joined, and see you next time.
Thank you.